Okay. Yeah. Okay. A question was raised this morning by Troy that I didn't answer, which was, I mean, at first all they knew about benzene was equal numbers of carbon and hydrogen atoms. But how do they know that it's 6 of each? Well, they didn't really know that at first. The only way they could figure that out was on the basis of the kind of information we covered later in class, like when you start substituting bromine atoms and then you measure, okay, the relative weight of bromine versus hydrogen and carbon, and then the number of isomers, it turns out to be consistent with all the information they had at that point. Then they could figure out, oh, there have to be 6 carbons. Okay, so I mean, you can convince yourself that they could figure it out that way. I'll leave that as an exercise. But until you know, as long as you only have the benzene, and you just do the analysis and break apart the carbon and the hydrogen, all you know is equal numbers of carbon and hydrogen atoms. It's when you start doing the other chemical reactions and then counting up the number of isomers that you get the clues that you need to figure out, oh, there have to be 6 carbons.
How would they be able to just substitute bromine out, just substitute bromine in?
Oh, I don't know exactly how. I mean, I'm sure that when they do that chemical reaction, they probably don't just end up with the monobromine or just end up with the dibromines. They're probably kind of mixed together when they react the benzene with the bromine. But then they can separate them out. Okay. Well, one of the other, I want to continue now telling you everything that this young chemist, Van't Hoff, was able to explain with his 3D molecular models. See, this guy actually took a lot of flack for doing this work, because at the time there were chemists who said, you know, Van't Hoff is taking this whole atomic model too seriously and thinking he can actually work out all these molecular structures, and that, you know, atoms are like, you know, children's building blocks, and you can just understand their geometry this way. That to a lot of scientists, that seemed like taking these atomic models too seriously. Well, Van't Hoff showed that you should take them seriously because they're the truth. And he was able to explain a lot of stuff that these skeptical chemists couldn't explain. And one thing he was able to explain was a strange fact concerning one of the chemicals in our bodies, lactic acid. And I told you at the end this morning that lactic acid is a compound that has a carbon in the center, and then it has 4 different groups hanging off this carbon. So it's got, you know, one of them is a OH group, an oxygen attached to a hydrogen. One of them is just a hydrogen. The other group is a carbon attached to 3 hydrogens. And then he's got a carbon, 2 oxygens, and a hydrogen on this last group. So now it looks like kind of a complicated molecule, but it's the same basic structure, the tetrahedron that we talked about earlier this morning. Troy.
Could you write CO2H, or do you have to write COOH?
Oh, actually, it's better to write. Chemists always do it COOH because if you write O2, there's sort of an implication that the two oxygens are hooked together, and they're not here. Yeah.
How would you do the molecular structure of COOH? What would it look like? Because
It actually looks like that. Okay. So you can see how complicated these things get. Now, but the reason I'm telling you about this one, I mean, this is an important chemical in the body. Like I say, it's the chemical that when you get really tired, your muscles kind of lock up on you. That's because you've got too much lactic acid in your muscles. Well, but what chemists discovered was that there's two forms of this lactic acid that have the exact same chemical makeup, and yet they're different. One of them actually reacts with the enzymes in your body, and the other one doesn't. Yeah, Drew.
how do you get rid of the lactic acid?
There are normal chemical processes in your body that break it down. I mean, if you rest for a while, your muscles get back to normal.
Is there any other way you can get rid of it?
I mean, there are enzymes that basically break it down and get rid of it, but yeah.
I thought if you rest, then the lactic acid goes up, and it kind of hardens in your muscles. So you have to like walk it off or something before it goes away.
Yeah, I guess if you exercise hard and then just stopped completely.
Then the lactic acid.
Yeah, you're probably right. Yeah, because then you get stiff. All right. But the puzzle for chemists was, why are there two of these things? And Van Hoff figured out, just with simple models. I mean, if you take let's say a black ball that represents your carbon, and you stick 4 different colored balls off of that central carbon, in this, so 3 prongs here at the bottom and then one sticking up the top in this tetrahedron shape. If you do that, and then you do it again, okay, so you have 2 identical models like that. If you take one of those models and you switch 2 of the colors, you'll find that they're not superimposable on each other anymore. They're mirror images of each other. Okay, maybe Mr. Van Dam can show you that with actual 3D models. I don't have any today, but it's just like the case of your right hand and your left hand. Structurally, they look the same, but they're not superimposable on one another. If you hold a right hand up to a mirror, it looks like a left hand, right? But you can't fit a right hand into a left-handed glove. And that's what's going on in your body. That it's only one version of this lactic acid that can react with the enzymes in your body, so that is functional, in effect. There's the other form of it won't react, won't do anything. So, and Van Hoff, by showing that, with this kind of a structure, you can get these 2 mirror images that are not superimposable on each other, and he could explain the different properties, and how one of them could react in the body while the other one didn't. Okay, so, and by the way, this is common in organic chemistry. There's a lot of molecules that have these mirror image partners, and only one of them actually works in the body, because the enzymes are sort of like the left or right-handed glove, and they'll only take one. Okay, so that's something else Van Hoff could explain. Now, let me see. I think I had one other example that I was going to give you. Let me. There's two acids, fumaric acid and let me switch markers here. Something called malaric acid. And they have the exact same chemical components in the same proportions. What? Oh, oh no, actually I mispronounced it. This is actually the way it was written in the book. Maleic acid. Okay. But here's the structure that they found. Again, you've got one of these COOH groups attached to a carbon, which is attached to a hydrogen, double bonded to another carbon. Okay, there's one, and then you have something very similar, except in the second case, you've got, in the one case, if you just look at the center of this molecule, okay, you've got these two carbons that are double bonded to each other. And then each one of them is attached to a hydrogen on one side and this COOH group on the other. But in the case of maleic acid, you've got the hydrogens on the same side and the COOH groups on the same side. Whereas in the fumaric acid, you've got them reversed. Now, so these are two cases of isomers. And the reason, one of the reasons I thought this was also discovered by Van Hoff, but I think what's interesting about this case is that he was able to figure out which of these acids must have the COOH groups on the same side, because this acid, the maleic acid, undergoes a reaction, a chemical reaction, that this fumaric acid doesn't happen in this case. Turns out that you can, if you heat up this acid in the presence of certain what are called dehydrating agents, it will steal a water molecule from this acid. See, notice you've got a hydrogen hanging on this end, and you've got an OH group hanging on this end. Those two can combine to form a water molecule and leave this this molecule. Yes, Daniel.
Doesn't that leave carbon dioxide and carbon monoxide too, also on the same side?
Yeah, I'll show you what happens. What you end up getting, what's left, is you actually get a compound that is,
No, you have to double bond the H's too. Oh.
hang on.
What about the
Yes.
left? See on the left,
Yeah.
down the bottom carbon. Oh, okay.
So you can actually form this thing plus, a water molecule. Now, like I say, only maleic acid does this. Fumaric acid doesn't, and you can see why it doesn't. Because these two groups, if they're in close proximity, you can have this this reaction, because it turns out that this group hangs on to its hydrogen really loosely, so that hydrogen can come off easily and end up combining with this OH group. But if the two COOH groups are on opposite sides of the molecule, then that doesn't happen.
Yeah, but there's a hydrogen on that side too.
There is a hydrogen on this side, but the carbon doesn't give up that hydrogen very easily, whereas this one will. So you can see why there would be. I mean, obviously, you have to know more chemistry than I'm able to tell you in this class to really see exactly why this happens and how it happens. But it's an indication of how. My only point here is by working out these structures, chemists were able to come to understand why, this acid will undergo certain reactions that this one won't undergo. Okay, so the middle of the 19th century, and the middle to late of the 19th century, was really the start of molecular structure chemistry, where at that point, we've seen that the atomic theory of matter was basically proven in by the end of the 1860s anyway, and and at that point, chemistry has really reached a milestone here. They're starting to understand complicated compounds in terms of their molecular structures. There's really, if you look at the chemistry that we've studied in this class, there's two huge milestones in the history of this science. The first, somebody tell me what the first one was. Evan. Yeah, it was the work of Lavoisier, because remember, before Lavoisier and the chemists of Lavoisier's time, there was a lot of speculation and talk about what substances were elements and what substances were compounds, but nobody had an objective method to prove, this is an element versus this is a compound. And Lavoisier did that by introducing this quantitative method where you carefully measure the products and the reactants. And then he introduced this whole new nomenclature in chemistry where the names given to compounds actually reflected exactly what they were made of. And so at that point, chemistry became a systematic science where there wasn't just a lot of empty debate and speculation. You ask a well-posed question, there was a way to answer it objectively. You didn't have to sit around and debate about it. So that's when chemistry became a science. But the second major milestone in chemistry, Dan.
J.J. Waters.
Oh, well, he was a key to proving the atomic theory, but he was a physicist. And what I was going to say as a broader point, as far as the major milestone in the 19th century, was coming to understand chemicals in terms of their atomic structure. Because Lavoisier didn't have an atomic theory. He just had an objective way of identifying elements and working out weight proportions of elements in compounds. But he didn't know that, that everything was made of atoms and that you could understand the properties of these compounds in terms of their molecular structure. And that was the great milestone of the 19th century. You know, by in the second half of the century, you see chemists being able to work out structures like this. Okay, now that is all I'm going to say about chemistry in this course. We're going to go back to physics now. Now, physicists are, I mean, these molecules we've been looking at, you know, from the physicist's point of view now, you know, that's the big stuff. The problem, I mean, molecules are small, but the problem that physicists still have to solve is what exactly is an atom? There's evidence already that atoms are not they're not elementary. In other words, they're not the very smallest building blocks of matter. They must have some structure to them. And we've seen hints of that so far. I mean, just the fact that the molecules, I mean, the atoms tend to be integer multiples in their weights. Remember, it makes you think that, oh, maybe they're built up of building blocks, and that's why they're these integer multiples of weight. I mean, it seems like a hell of a coincidence that carbon is exactly 12 times heavier than hydrogen, that oxygen is 16 times, nitrogen is 14 times. I mean, why these round numbers? Also, remember, Faraday in his electrolysis experiments showed that there was this relationship between the number of atoms interacting and the amount of electricity produced. And for if you took a certain atomic weight of atoms, for instance, 1 gram of hydrogen would produce exactly so much electricity when it reacted. Well, that same number of lead atoms, when it reacts in a lead storage battery, produces exactly twice that much electricity. Okay. So it's like there was even they were seeing integer multiples associated with the electricity that atoms would give off. So it makes you think, well, maybe there are some smaller building blocks here that the atoms are made of, but nobody knew anything about them yet. Okay, so that's what I want to get to next. So let's focus. I'm going to call this section the discovery of the, any guesses? Daniel?
I'm not sure what the broader group is, but it's protons, neutrons, and electrons.
Yep. Electrons came first. Okay, now let me, I'm going to start out telling you about an experiment that was done by a guy, William Crookes. Unfortunate name. Crook or crooks? Let me see. I can't believe my book doesn't have his name. I think there's an S on the end. Okay, so, and he did, let me see, I think he did this experiment in 1879. Or at least that's when the paper was published. Now, he noticed that if you have an electric field in a glass tube, and that the air has been pumped out of, you can draw what you'll see is something is coming off like if you have a negative electrode stuck into one end of that tube. So you got a glass tube. Let me at first just make this real simple. Okay, you got a glass tube and a negative electrode stuck in there. Well, let me go ahead and complete the whole setup here so you can see what's going on. Okay, so you have a negative plate here. Let's put the positive plate over here someplace. And okay, is an air pump, so you're pumping all the air out. And you have a little partition here with a hole in it. This is negative, and this is positive. Okay. Any ideas on what might happen in this setup? Yeah. Actually, they do spot some current. If you put an ammeter in here, I mean, you might not expect much of a current, but in fact, you do get one. You not only get a current, but you get, when there's still a little bit of air left in here, you'll see the air kind of glowing a little bit. And yeah. And then if you take almost all the air out, the glow disappears, but you see a bright spot over here against the end of this glass. Now what's going on? Well, one key to what's going on is if the size of this bright spot depends on the size of this hole here. If you make the hole twice as big, bright spot's twice as big. Okay, so that tells you something. Tells you that there's something going from this plate over and hitting the glass on the end and causing that bright spot. Nick?
You took out that divider with the whole end being little.
If you took out the divider entirely, what you would get is a bright spot the size of this plate. Okay? Try.
Is the divider, can the divider conduct electricity, or is it insulator?
It's I think it's an insulator. Yeah. So basically it's just blocking. What's happening is that something's coming off this plate and flying down this tube. Now, when you have some air in there, whatever's coming off this plate is hitting those air molecules and causing them to emit some light. So that's why you see the gas glowing when you have air in. But when you take almost all the air out, okay, obviously the glow is going to go away. But obviously whatever was coming off this plate is now hitting the end of the tube. Now, how are you going to figure out what's coming off that plate? Well, one thing that that Crookes thought of doing. Oh, by the way, because this bright spot on this end of the tube is just the size of this hole, and then as you increase the size of this hole, the bright spot gets to be as big as your little electrode here, but then no bigger. You can also know that whatever's coming off this thing has to be coming off in straight lines. Okay, it's not just flying out in all directions like light from a light bulb. It's shooting off in straight lines. Now, one question you might ask yourself is, well, there's some evidence actually that well, let me start again. If you suspected that these whatever's coming off here had electric charge, what would you do to test that? What's the simplest thing you could do to test it? Nick?
Hold it up to the microscope.
Oh, that's true. No, that's true. I mean, if you think that this end of the tube now is getting charged, yeah, you can hold an electroscope up. That's not what Crookes did. Crookes did something that's probably even easier for him. He just took a magnet, and let's say you've got a bar magnet, and you approach the tube with the north pole of it. Okay, so what's that going to do? That's going to put a magnetic field going into the board here, right? Yeah, if you just like approach it from the side, pointing the magnetic pole, the north magnetic pole into the board here. Now, what's going to happen to your if whatever's going down, traveling down this tube, is electrically charged? What's going to happen? How well do you remember your laws of electricity, your magnetic force law? Okay, you got the right hands going. What the force law was, I crossed into B, right? So, I mean, if we had positive charges going down here, then we'd have a current going in that direction, right? And it'd be deflected up, right? That's the I point your fingers in the direction of the current, curl them in the direction of the magnetic field, and your thumb points in the direction of the force. Remember?
Oh, because it goes. Oh.
Right. So if it's positive charges that are flying down this tube, okay, you would expect when he holds his magnet up to it, the beam is going to go, you know, it's going to hit the top of the tube now. Okay? Negative charges, yeah, it's the other way, because that's like a current going in this direction. It's going to go down. It's going to go down. So what does he see? You had a 50-50 chance. Negative. Actually, you had better than 50-50 chance. This is a negative plate, right? So you would expect negative charges to come off of it, maybe. But Crookes, he tests it. You know, he holds his magnet up there. Sure enough, this light spot that had been hitting the tube here, you know, moves down and is hitting down here someplace. So now he's got good, solid evidence that with this setup of his, what he's actually seen here is a beam of negatively charged particles. Okay. So now these, what he's actually seen here would eventually be given this name, electrons. And but this was as far as Crookes actually took the situation. He created this beam and showed that it had to be consist of negatively charged particles. And this was a brilliant experiment. This was not at all easy to do. The reason that people hadn't done this kind of thing before was because it does require a really good vacuum. You have to take out, well, there can't be more than about 1/1,000,000th the amount of air left in this tube. So that means you really have to have a great vacuum pump. But by the 1870s, scientists knew how to make such things. So he could get an excellent vacuum pump, and then he had this great assistant that built these incredibly strong glass tubes, because otherwise they'd crush, right? So this is another one of the great secrets to being a famous, successful scientist, to get yourself a really good assistant to take care of the technical details like that. So anyway, he gets credit with being the first to produce these things that actually at this time were called cathode rays, because the negative electrode Faraday had called the cathode, and these were rays that came off the negative electrode. So next week I'll tell you about the guy who gets credit for actually discovering the electron and determines its charge to mass ratio.